welcome everyone to the fourth Direct Write lithography workshop and its RIEH webinar series. Before we listen to Christoph, a few acknowledgements I'd like to make. First, I'd like to recognize the traditional owners of the land we are gathered here today, or at least for my case, which are the people of the Kulin Nations. And I'd like to pay my respects to their elders, past, present, and emerging. And then, of course, I'd like to acknowledge our head organization, the Australian National Fabrication Facility, ANFF, and its CEO, Jane Fitzpatrick, for the ongoing support. Furthermore, I'd like to acknowledge our panelists who helped to facilitate this webinar series. A few of them are actually also online, which is very nice. Thank you for joining us. And lastly, I'd like to give a big thank you to the whole organizing committee for their hard work in making this webinar series possible, and of course the workshop as well. And with that, I'd like to introduce our speaker, Christopher Vallee from the University at Albany. He will talk about 50 years of reactive ion etching in microelectronics. So before I let you start, Christoph, I'll go through your bio very quickly. Christopher Vallee received his PhD degree in physics from the University of Nantes in France. I hope I pronounced it correctly, in 1998. Yeah. His research activity focuses on plasma and atomic scale processes. He's currently a professor at the College of Nanotechnology, Science and Engineering, CNSE, University at Albany in the USA. Until September 2020, he was a professor at Grenoble Alpes University in France and a visiting professor at Tsukuba University in Japan from 2016 to 2020. Also in 2026, he will chair the ASD workshop and the ALE workshop of the ALD/ALE 2026 conference in Tampa, Florida. And with that, Christoph, I'll hand over to you. Please share your screen. I'll stop sharing mine.
Okay.
Yes, we can see your screen.
Yeah. You good?
Perfect. Perfect.
Perfect. We can start. So just trying to get. Where is my pointer? Okay, so I did a presentation on about 50 years of reactive ion etching. The idea is to show the evolution of the etching processes and the etching reactor, going from what I wrote here from the plasma RIE with a continuous wave of, so where we just change the design of the reactor to pulsing plasma between at the beginning of this century, and now going to pulsing everything to go, for example, to atomic layer etching. So I will try to illustrate the evolution of the processes and the reactor from the beginning to now, and I will try at the end to give some description of what we can probably work on for the next 5 years or next 10 years. So this is the outline of this presentation. So first I will try to have a very fast history at time scale of RIE. And I will try after to show you how to correlate with the scaling of these transistors. For example, we can do a good correlation between the scaling of the transistor and the evolution of the plasma etching processes and tools. So first, just to introduce Albany. So I'm professor at University at Albany. So Albany is here. So Albany is in the New York State. So it's about 2 hours and a half by car from New York City. It's about 3 hours to Boston and 3 hours and a half to Montreal. So Albany is a New York State capital, and this is where I'm doing my research. This is at the College of Nanotechnology, Science and Engineering. And the department I am here is inside what we call the Albany Nanotech Complex. And so Albany Nanotech is where you have the 300mm fab for R&D with IBM, Tokyo Electron, Applied Material. And this is where, for example, IBM is doing the first gate-all-around transistor and so on, because this is where we have in US, for example, the first extreme UV lithography. And so this is a description of all the square feet we have for clean room and the number of people, scientists and engineers from industry and academy on site. So it means it's very nice for our students here at the college because they can go to the clean room and they can do some internship and summer work with our partner for semiconductor. So now let's start about reactive ion etching. So I just did 2-3 slides at the beginning just to remind what is the benefit of plasma etching and what reactive ion etching is was very useful for semiconductor industry. So this is some basic slide we may use in any plasma lecture for a plasma etching, where we want to talk about the two important parameter we need to control when we do an etching process. We need to control the selectivity. We need to etch one material and not other material like the mask or the substrate. And we need to control the anisotropy, for example, if you want to etch only in one direction. So we can use different etching, and you can have a pure chemical etching, like a wet etching. If you have a pure chemical etching, it can be very fast and very selective due to the chemistry. But usually it's isotrope, so you are etching in all directions. But you can use an ion beam etching, so you only sputter with ions, so it can be highly anisotrope because ions will come perpendicular. But usually you don't have chemistry, so you don't have selectivity, and you may have a lot of damage. So this is why plasma etching is very useful, because in a plasma process, you have both chemistry with radicals and both ions, so you can combine the benefit of the wet and the benefit of the ion etching to have a fast anisotropic with etching with a good selectivity. So when we do plasma etching, you all know that we need to etch. So we need to form from a solid a spontaneous volatile byproduct. So this is a basic of the chemical etching. So we just want to have a plasma, and we do, thanks to the plasma, we do an interaction with the solid, and we want the final product to be volatile. So for example, we use some fluorine containing gas like SF6, and we use a plasma to make this stable molecule to create some radicals, so to extract from the molecule some etching agent. And then the fluorine atoms can react with the material, like for example, the silicon, and form silicon-fluorine bond. And when 4 fluorine atoms are attached to the silicon, SiF4 is not solid, so we have a volatile byproduct, and so it's not solid, so we have volatile byproduct, and we are etching the silicon. So this is a chemical etching. So for chemical etching, this is the first step we do when we do plasma etching. We need to understand what can be the volatile byproduct. So depending on what product can be volatile, for a given solid material we want to etch, we have to select the gas we will use for the etching. So if you want to make a SiF4, you have to select a fluorine-containing gas. If you want to make a SaCl4, you select a chlorine-containing gas, and so on. If you want to etch aluminum, aluminum fluoride is not volatile, so you will etch only with chlorine, for example, to make a volatile byproduct. If you want to etch a polymer, you use oxygen to form CO or CO2 and water, volatile byproduct. So it's the first step for any plasma etching process, just to understand what can be volatile for etching a solid, so we can design the gas we can use. What is very interesting, in fact, is that in 1974, a Japanese group found that we can enhance the sputtering of when we want to do the etching. If instead of doing sputtering with a rare gas, we can do sputtering with ions. And if we have chemical ions, then we can enhance the sputtering. So this is a first paper when people observe that by using ionic assistance with a chemical, we may enhance the etching rate. This is the beginning of reactive ion etching. And you can see a huge improvement of the etching rate compared to pure argon when you use some ionic, chemical ions. And this is a reactive ion etching, and this is easy to understand with the work that everybody is using to explain the RIE for any plasma class, the work from Coburn and Winters. When they expose a silicon material to only an etching gas like XCF2, so they have a pure chemical etching. They expose the same material to pure ions, so you have only sputtering. And when they expose the same material to both the chemical etching and the ions, so when they have the reactive ion etching, you have a huge increase of the etching rate. So thanks to the ions and the neutral species at the same time, we have a synergetic effect, and we have a huge increase of the etching rate when the surface is exposed at the same time to both the chemical agent and the ions. So this is how we can have an anisotropic etching. So I can take an illustration. Imagine you want to etch silicon with a fluorocarbon process. And for example, when you have both ions and fluorine, you etch at 60 angstrom per minute. And when you have only fluorine species, you etch at 5 angstrom per minute. And you want to etch 60 angstrom of material. So as you will start to propagate, you will start to propagate the etching in this direction at the rate of 60 angstrom per minute because you have both. While at the edge, you don't have ions, you have only the radical species. So you etch at 5 angstrom. So when, at the end of your process, when you will remove the 60 angstrom, you will only remove only at the top, for example, 5 angstrom. So you have a not perfect, in this case, anisotropic profile, but nearly perfect anisotropic profile. So we have many tricks to have an anisotropic profile, like modifying the etching chemistry, playing with temperature, blocking the sidewall etching, like doing a passivation of fluorocarbon at the edge, and so on. But I will not discuss today. This is not the aim. What is very important is that we found, so thanks to this first publication, we understood that it may exist a process that we call RIE, where you can easily etch in one direction very fast and being still selective. And so this is the beginning of all the history of RIE. And here I gave a sort of timeline of all of some important research and publication. And I will extract some of this publication later for my presentation to explain that after this first concept, many people try to understand how we can improve the RIE process by playing with the frequency of the generator, by using, for example, ICP source, by having an independent RF biasing, by using cryo, by using dual frequency, and so on. So people during 20 years try to understand the plasma etching and understand the impact of the plasma design and plasma parameters on the RIE. And here is the same timeline with the tools that were commercialized by industry. So you can see that I found that maybe I'm not right. Maybe you have before that, but I found that maybe one of the first industrial array tool was developed by Lam Research in 1981. This is the Auto Etch 480. And you can see after that, Applied Material TEL also developed array system. Hitachi was the first to use a microwave plasma etching system and not CCP design with a single frequency. In the 90s, you can see that it's when we started to introduce HDP source, like with the ice inductively coupled plasma system. And here at the end of the 90s is where we started to introduce a dual frequency plasma etching process. And after we started to introduce pulsing capability, pulsing the plasma, pulsing everything like the atomic layer etching system. And the last generation of plasma etching reactor is to use cryogenic etching. So I can take this timeline with the generation of reactor from industry and select in 3 timelines. And I will discuss today the 3 timelines. The first timeline is that we change the design of the reactor, but we still have a continuous plasma process where the power is always continuous and the precursor is always introduced in a continuous way. And after here, we have the second type of design where we started to pulse. We started to first pulse the plasma, and after we started to pulse also the precursor and the gas. So going from plasma pulsing to ALE, for example. And now we have the new set of generation of reactor, and maybe we have to play with new parameter we were not playing before, like for example, going to low temperature. So this is the end of this very fast introduction, and now I will talk about the first design for the geometrical scaling. So this is something I did, and I like this is what we have for the transistor. So we have 3 area for the transistor. We have the first scaling area that was a geometrical scaling for the transistor to follow the Moore law. So where we did always the same transistor, but we just reduce the size of the transistor, the dimension. So same silicon silicon oxide polysilicon transistor, but what we do, we only reduce all the dimension to be faster. So we have a size reduction, so what we call geometrical scaling. So scaling was done thanks to lithography. And after, we add what we call the equivalent scaling when we introduce new material and we started to go from the 2D to 3D devices. So new material like the high K, and so with the high K, where we add an equivalent oxide thickness. This is why we can talk about, for example, equivalent scaling. So it's a second generation of a second scaling area. And from IRDS, it said that since this year, we are entering the third scaling area for the transistor. This is a 3D power scaling, because now we go to complete transition vertical structures. So what I want for today, what I did is that I tried to identify the etching process and the evolution of the etching process corresponding to each scaling. So for example, for the first scaling, we can say that, as I said, all the process were continuous. So we have the continuous flow of precursor, continuous wave. So the power is always on for the generator. But what we did, we tried to modify. So we play on the process chemistry. So today I will not talk about the chemistry, trying to understand fluorocarbon, I think the next speaker will explain all the chemistry of the plasma etching. Today I will try to focus on the design of the reactor, going from single frequency CCP reactor to high density plasma reactor and dual frequency plasma reactor. So to understand why we did this evolution of the design, I just tried to go back to very simple understanding of a plasma etching process. So when we do a plasma etching process, we have the ion-assisted etching. So if the process is mainly based on the ion-assisted, so the etching rate will be proportional to the ion flux and the ion energy. And we have the chemical etching process. And for the chemical etching process, the spontaneous etching depends on the radical flux and temperature. So these are two main parameters every time we have for chemical etching or ion-assisted etching. So when we add the very first generation of plasma etching reactor, I will say single frequency CCP plasma reactor. So you apply with a single generator, you apply a power. With this power, you will fix the plasma density. So you will fix the ion flux and the radical flux. Usually the temperature is fixed. And depending on the power you apply, you will also fix the DC cell bias. So you fix the ion energy. And each time you will modify the power applied to the substrate, if you increase the power, you increase the ion flux, but you also increase the ion energy. So it means that the parameters are coupled. You cannot only increase the ion flux without increasing the ion energy, or you cannot increase the ion energy at the same time as you decrease the ion flux. So all parameters are coupled, and all parameters will not vary with time. So we can understand that maybe in processing point of view, to improve the capability of the process, maybe we could say, can we uncouple some parameter, or can we modify some parameter with time during the time of the process? So this is where, and now I'm go back to some of the literature that was done with very important paper to try to understand how we can modify a plasma reactor. And the first paper I will take is this one from Australia, from Ron Boswell and Perry, so from Australia, who are first, to my knowledge, to show that we can have a fast anisotropic etching with an ICP source. So now we have inductively coupled plasma reactors. So we do the plasma thanks to the inductive field and not the capacitive field. And we have an independent bias of the substrate. So we have two power, one for the plasma density and one to control the ion energy. And then we may have very good anisotropic etching, and we can also apply an independent bias to control the ion energy. So they were the first, to my knowledge, to demonstrate this fast anisotropic etching with an independent RF substrate basing. And this is the idea of all what we call HDP source or inductive source, because it's mainly inductive, but a microwave system can be put in the HDP source, where we have now an independent control of ion flux and ion energy. So the idea is that if I go back to this device, with this power applied to to the coil, so what we call the power source, you will fix the plasma density, so you will fix the ion flux. And with the power applied to the substrate, you will not modify the flux, but you will modify the DC cell bias of the ion energy. So you have a power bias to control the ion energy and a power source to control the ion flux. So now you can increase the ion flux without increasing the ion energy by playing, for example, with only the power source, or you can increase the ion energy without increasing the ion flux by, for example, playing with the bias power. So you have an independent control. So this is what is illustrated here with this extract from this paper. You can see that, for example, here you have the plasma density. So, and if you increase the source power, so the power applied to the coil, you increase the plasma density. But if you increase the bias power, so to increase the ion energy, you do not modify the plasma density. So the bias power has no impact on the plasma density, so the ion flux, but the bias power will have an impact on the DC cell bias voltage, so will have an impact on the ion energy. So the value of the DC cell bias you will extract of the ion energy will depend on the source power. Usually, denser is the plasma, lower is the cell bias voltage. So because if you apply a bias power, the power is a product between the voltage and the current. So when the plasma is dense, you have a lot of current going to the substrate. So if you have a lot of current going to the substrate, you need to develop less voltage. So at the end, the DC cell bias is less compared to the DC cell bias with 500 watt. Here, this paper is just to show that it's not perfect. The decoupling is not perfect. To have a perfect decoupling, you have to pay attention to the ratio between the bias power and the source power, but you have a decoupling. So it means that we may have a new design for the etching. Instead of using a single frequency CCP reactor, we can use what we call HDP source. It's a new design with inductively coupled plasma to have an independent control of ion flux and ion energy. So it was a second generation of plasma etching reactors that were used for semiconductor industry. So this is a second generator of plasma reactors that were used by semiconductor industry, like the applied DPS chamber with the coil all around the dielectric window here, and you have an independent control of the substrate, or the LAM TCP reactor, where you have the coil here, and so you apply the source power to the coil, and you have an independent control of the energy here with the bias applied to the substrate. So what is interesting that now we decouple the ion flux to the ion energy with this design. Okay, so it's nice design, but the main issue with the HDP source is that since the plasma is very dense, it can be very difficult to have very energetic ions because the DC cell bias you will develop is not so high because you have a high ionic flux. So at the same time, the question is, can we still keep the CCP design, but try to have a decoupling with the CCP reactor? And yes, we can have a decoupling with CCP reactor by playing with frequency. And so I go back to my timeline and I will take this paper where we have the frequency impact on RAE. And this is the first paper from Robert Bruce. And you can see that in this paper, he studied the frequency dependence for etching with CCl4. And what he observed for silicon etching, that if we change the excitation frequency of your single frequency generator, so it was a single frequency CP, if you go from low frequency to high frequency, as you go to high frequency, you have a huge drop of the etching rate. So he observed a very huge drop of the etching rate, and the drop of the etching rate was explained by the fact that the energetic ions, the energy of the ions is decreasing. So he observed that when we go to very high frequency, we decrease the energy of the ions. And in addition, with LAM, for example, at the same time, and Dodeni did also a lot of paper to try to understand the impact of plasma frequency or frequency generator on the plasma properties for the etching. And what they found that depending on the frequency, if you increase the frequency of generator, you increase the plasma density, so high frequency dense plasma. But if you increase the frequency generator, you decrease the peak-to-peak voltage. So at the same time, you decrease the ion energy. And so you decrease the etching rate, as was observed by Bruce. And you not only decrease the ion energy, you can also, with the frequency generator, modify the shape of the ion energy distribution function. And if you have a high frequency generator, you have low energy ions with a narrow distribution. While if you use a low frequency generator, you have energetic ions with a large energy distribution. So to try to understand this shape, I did a very simple schematic. So first, for example, we use a 13 megahertz generator. So when we use a 13 megahertz generator, usually this frequency is higher than the ion plasma frequency of the ionic species in the plasma. So ionic species in the plasma, so if we don't consider very light ions like hydrogen, the plasma frequency is several megahertz, so it's lower than 13 megahertz. So what does it mean? I have ions in my plasma. They are at the plasma potential. I will apply to my substrate RF voltage, 13 megahertz. So my oscillating frequency is 13 megahertz. And I am oscillating around what we call a DC voltage, VDC, the DC cell bias. Since the frequency of the ion is very low compared to 13 megahertz, what does it mean? It means that, in fact, the time it takes for the ion to transit through the plasma sheath, so to go from the plasma to the substrate, so this is what we call in between the sheaths, the time it takes to transit the sheath is very long compared to the time of the oscillation because the frequency is very high. So it means that the ions are not sensitive to any instantaneous value of the peak-to-peak voltage. They are not sensitive. They are only sensitive to a mean value, so they are only sensitive to the VDC. So it means that in this case, most of the ions will come with only the energy that is equal to Vp minus VDC. So we have a narrow distribution, Vp minus VDC, for this case. And now if I go back to this case where we apply a low frequency generator, so if we apply a low frequency generator, so this frequency, for example, hundreds of kilohertz is lower than the ion plasma frequency. What does it mean? It means that now the transit time for the ion to transit the sheath is very fast compared to the time of the oscillation. So now the ions will take, as they transit, the instantaneous value of the RF voltage, and not the VDC. And so we have now a broad distribution of the ion energy because they can come from the minimum energy here to the maximum energy, and they can take all the energy in between. So we have a narrow distribution, but the energy of the ions can be much higher than the energy of the ions with a high frequency generator. So we go back, this is what we obtain, high energy compared to low frequency and large distribution, narrow distribution. So usually when we do plasma etching, we have multiple ions with different mass. So what you have on your substrate, you have ions coming with different energy distribution. And it can be very large for light ions, or it can be very narrow for heavier ions. I took here an example of different mass for different ion plasma frequency. So it has been observed that if we play with frequency, we can, by increasing or decreasing the frequency, we can have energetic ions or low energetic ions. So low frequency generator, high energetic ions, high frequency generator, low energetic ions. And we had the same with the plasma density, so with the ion flux. So what we can say is that the power absorbed by electron is found to be proportional to the square of the frequency and vary linearly with the RF voltage. So it means that for a constant RF voltage, for example, the plasma density, which is proportional to this number, will probably increase like the square of the frequency of generator. So if you increase the frequency of generator, you increase the plasma density, so you increase the ion flux. And so we go back to what was observed. What was observed that as you increase the frequency, you increase the plasma density. So it means that we have not we can see we have two opposite behavior of ion flux and ion energy with frequency. High frequency, more dense, but less energetic. Low frequency, less dense, but more energetic. So this is what we have, for example, for a fixed power applied to the substrate for a single frequency plasma etching process. If we use a high frequency generator, like for example, we use an 80 megahertz generator, we'll have a high ion flux. But since we have very high ion flux, the current flowing to the substrate is high. So for the same power, since we have more current, we develop less RF voltage, or less peak to peak. And if we develop less peak to peak, we develop less DC bias. So the ion energy is low. So ion energy is low. First, we have high frequency generator, we may have high ion flux, but low energy. But if we use a low frequency generator, so in this case, the low frequency is 13 compared to 81. If you use a low frequency generator, the ion flux will be less, the plasma is less dense, but since we have less current flowing to the power, to the substrate, we develop more voltage, more peak to peak, so we develop more VDC, so we have more energetic ions. So we see that we have opposite behavior of the frequency for the flux and the energy. But if you have a single frequency generator, you cannot decouple. So the idea is that maybe we can use a CCP and we can have two different generators where we can have a high frequency generator and we use a high frequency generator to control the plasma density, so the ion flux. And we have the low frequency generator to control the ion energy. So this is what we have. And here we have the first paper where people try to use this idea of doing a plasma array with two different radio frequency generators from this paper from Goto, where they use a high frequency generator at the top to control the plasma density and a low frequency bottom generator to control the DC cell bias of the ion energy, and they study the etching of silicon and silicon oxide using this system with a dual frequency process. And you can see again with this paper that depending on the frequency, so as I said, if you increase the frequency of the generator at the bottom, for example, you will develop less cell bias because you will develop less peak to peak. So it means that the DC cell bias is low. And we say that the ion energy is Vp minus the DC cell bias. So the ion energy will be low. But if we use a low frequency generator at the bottom, now we develop more DC cell bias. So we have higher energy. So it is better to use a low frequency generator to have high energetic ions coming to the substrate. And for the top electrodes, they also study that if they modify the radio frequency and they go to high frequency, they can increase the plasma density. And they look at how it will impact the cell bias. If they increase the plasma density, for example, for 100 watt to 300 watt, the DC cell bias will be lower for a given power to the substrate, and the ion energy will be lower because, again, if we have a more dense plasma, we flow more current, so the power at the substrate will develop less voltage, so less DC, so less energetic ions. So they have all the results that we had in HDP source, where we have an independent control of the plasma density and the ion flux, and denser the plasma, lower is the ion energy. So this is what has been found. So we found that radio frequency can modify the plasma density and ion energy, and the ion flux and ion energy can be decoupled using either a HDP source, for example, inductive system, or a dual frequency system. And so this is why we shifted from CCP plasma reactor to ICP or TCP plasma reactor or dual frequency CCP reactor. Now, instead of having all parameter coupled, we can decouple the plasma, I would like to say parameter, like the flux, to the substrate surface parameter, like the energy. So ion flux and ion energy now are decoupled. But we can see that with this design, we still have all parameters that do not vary with time. So this is some slide just to show the evolution of this plasma etching reactor during this first scaling area. So we went from first design with a single frequency CCP reactor that can be enhanced with magnetically enhanced, so to have more uniform plasma potential and etching rate on the wafer. And now we have the second generation of plasma etching reactor, which are HDP source, where we have, for example, inductive source, where we have an independent plasma density with the source power applied to the induction, to the coil, and the bias power applied to the substrate. So this is second generation of plasma etching reactor, HDP source. And we have the third generation, where we go back to the CCP design, but now we use two different frequency or three different frequency. And after the frequency can be applied only at the bottom, two frequency at the bottom, or one at the top, one at the bottom, or one at the top, two at the bottom. So depending on the tool maker, you have very different design depending on what you want to do and what you want to etch. You may have diode, triode, you may have different design. Here is an example of the evolution of the CCP platform from TEL equipment. So you can see going from the first single frequency generators that were used at high pressure. So with this first system, it was not using RIE, it was only high pressure, the substrate here. So we do not use ions. So it was isotropic etching. So it was the first system we were doing plasma etching before RIE, but it was mainly isotropic. So when we found the RIE and we can use ions, so we modify. Now we apply the power to the substrate to put some energetic ions. And after we had start to have dual frequency generator, and after the design is modified, now they have some superposition of DC voltage for ballistic electrons. You have two different frequencies at the bottom. You can pulse now the plasma. You can add some ALD in the chamber. So you have many evolution, but you can see an example of the evolution of the design of the CCP reactor for a tool maker like Tokyo Electron. So this is the end of the first part. Now we go to the second part, which is the evolution of plasma etching processes and reactor for equivalent scaling. For the equivalent scaling, this is where we introduce new materials and we transition to vertical structures. So we had the FinFET, for example, for the transistor. What we can observe that we started to pulse. So regarding plasma etching, we started to pulse. So we started to pulse the plasma. And after we started to pulse also the precursor. So the idea is that now we have a decoupling on radical flux and ion flux and ion energy. But I told you that all parameters are fixed with time. So the question is, can we change the value of the parameter during the time of the process? Can we modulate the ion energy during the time of the process? Can we modulate the ion flux during the time of the process? Can we modulate the radical flux during the time of the process? Yes, no, this is what we will see now. So this is the idea. So the idea is to try now to see, can we have a modulation with time, for example, of these two parameters that are the ion flux and the ion energy. And this is yes, if we start, for example, to pulse the plasma, so it means that the plasma, we don't have a continuous wave. So now plasma is sometimes on, plasma is sometimes off. So the power we apply to the source, sometimes we apply, for example, 500 watts, then we stop to apply the power. Then we apply again 500 watts, and we stop to apply the power. So we pulse the plasma source. And if we pulse, we can change the plasma properties with time. And if we change the plasma properties with time, we can modulate depending on the frequency. Usually we modulate the ion flux. We don't modulate the radical flux. And if we modulate the ion flux, we can also modulate the ion energy by pulsing or by also adding a pulsing of the bias. So we can also try to modulate the ion energy. And so at the end, by pulsing, we can modulate ion flux, ion energy, and the ratio between radical flux and ion flux with time. This is very good for high aspect ratio etching and, for example, to improve aspect ratio dependent etching. It's nice to be able to modulate this ratio. But when we pulse the plasma, the radical flux usually is still constant and the temperature is still constant. So if I go back to my timeline, you can see that the first time it was proposed to pulse the plasma with the ICP source was this paper. Again, I took this paper because it was maybe one of the first, or maybe the first, again, from Australia. So Rod Boswell from Australia did a lot of exciting work, very useful for plasma etching regarding plasma properties, so HDP source, pulsing, and so on. And in this paper, what they did, they were pulsing the ICP generator, pulsing from 1 millihertz to 1 hertz, and they were pulsing 1 megahertz, sorry, to 1 hertz. No, if I do the base duration, sorry, yeah, 1 hertz, and yes, 1 millihertz, and the duty cycle was 20%. So 20%, it means that the During the plasma on, the plasma is on during 20%. So if, for example, the pulse duration is 1 millisecond, so 20%, it means that during 0.2 millisecond, we apply the power, and during 0.8 millisecond, we don't apply any power. And they observe that depending on the duty cycle and the frequency of the pulsing, we have no modification of the etching rate compared to a non-pulsing plasma, or we may have a strong modification of the etching rate compared to a non-pulsing plasma. And they observe that the drop of the etching rate is explained by a concomitant decrease in the energy of etching particles. So they say that as we pulse, we decrease the improvement, the RIE effect is decreased because we decrease the energy of ions. So in fact, what we know right now is that if we pulse, all the species in the plasma don't have the same decay. So they are surviving more or less longer in the off state. And so, for example, electrons, usually when you start, so you have your plasma. When you start to apply the power to your plasma, you will lose very fast your electrons. Then the decay of ions take more time. And for radicals, usually they survive very long time. So it's why I'm saying that when we pulse, usually we don't really modify the radical flux because radical can survive a very long time, like for example, 50 milliseconds. And usually the pulse we use for the process is about 10 kilohertz or 1 kilohertz. So at the frequency of the pulse, radical are surviving during the off time. So radical flux is always constant, even when we don't have any power. But as we pulse, we can lose the ions and we lose the electrons. So if we lose the ions, it means that the ion flux will be modulated and we'll have less ionic flux during the off time compared to the on time. So we will, and if we have also less ion flux, we can also modify the DC cell bias and we can modify the ion energy. And we can also modify the ion energy by pulsing the substrate. So we can have a radical versus ion flux that is modified between the on and the off, and the ion energy that can be modified between the on and the off. So usually when we have a HDP source or a dual frequency process and we want to pulse, we have different way of pulsing. For example, we can only pulse the source and we don't pulse the bias. The bias can be continuous. Or we can pulse the bias and not pulse the source. Or we can pulse both the source, so the power source applied to the coil for the HDP, and the power applied to the bias. So we may, and when we pulse, we can pulse in synchronous, so we can be asynchronous, so we can have some delay between. So we have different way of pulsing. For example, we can pulse only the source, we don't pulse the bias. Or we can pulse only the bias, we don't pulse the source. We can pulse source and bias in synchronous pulsing, or we may have some lag in between. So we have this, it can be very complex. So it means that we may have a strong modification of the plasma. I mean, when I said the chemistry, it's because usually when we pulse, since we have a lot of offset, we are more molecular species and atomistic species. So usually we observe a modification of the chemistry of the plasma with more molecular ions or molecular radicals and atomic ions or atomic radicals. And we also modify the ion energy and the distribution. So if you decide just to pulse the source, usually the source is pulsed just to modify the ion flux versus the radical flux. When we pulse the substrate, the idea is to modify the ion energy. So we can synchronize, we can be in phase, out of phase. And so we can try to, depending on what we do, for example, to increase the etching rate thanks to the pulsing, or we can try to have more energetic ions. Because, for example, if you pulse in this way, for example, now you have the off time. And if or you can pulse with high power, low power. And if you have a low power and you bias, since you have a lower ion flux going to the substrate, you develop more DC cell bias, so you will be more energetic compared to the case you had a continuous high power source. So now you have more energetic ions. So you may be in the case where you can have very high energetic ions going to your substrate. So this can be good, and you can improve all your plasma process. So you can improve etching rate, selectivity, aspect ratio dependent etching, all the different issues you may have, but it can be also be bad sometimes. So it's very good regarding you have more knob, more parameter to tune, but for a process engineer, it starts to be very complex to understand the plasma process because you have more and more parameters. Now, we go from single frequency CCP generator where we have only to play with the flow rate, chemistry, pressure, and source power. I mean, it was what we only had to modify. Now we have HDP source when we have flow rate, pressure, chemistry, source power, and bias power. And now we have the same when we pulse the source power, we pulse the bias power. So it's more complex to optimize, to develop BKM and understand your process. So now you need really people to be expert in plasma etching to understand. And this is an example of how you can improve aspect ratio dependent etching. So aspect ratio dependent etching is usually because depending on the aspect ratio we don't have the same number of radicals going in the trench. And since we don't have the same number of radicals, we don't have the same etching rate depending on the aspect ratio. So when you have high aspect ratio, usually you have slower etching rate compared to low aspect ratio. But now if you pulse, you can play with the pulsing to try to compensate. And during the off time of the pulse, you will have more radicals than ions. So you can compensate here and try at the end to have no aspect ratio dependent etching. So whatever the feature, high aspect ratio or low aspect ratio, you etch at the same etching rate. This is another example for low-K etching. For example, if you pulse, depending on how you pulse, you can modify, for example, the concentration, ion flux, and concentration of species at the surface. And if you modify the concentration of species at the surface, you may modify the threshold energy for the etching. And if you modify the threshold energy for the etching, for example, for porous low-K, you can modify if you don't pulse, depending on depending on your duty cycle. So if you do not pulse or if you have 25% of duty cycle, you will modify the bias voltage you need to start to etch the porous low-K. So if you modify the threshold voltage, now if you want to have a selective process between low-K and silicon dioxide, you can modify your selectivity by pulsing, and you can see that you may have a huge modification of selectivity and go to the pulsing to sort of infinite selectivity when pulsing for in this example, a CHF3 plasma. I will not talk about chemistry too much today because I think you will have other later for chemistry, but if you have to just keep in mind something, usually when you pulse, you change the fragmentation also of the plasma. So your plasma, when you pulse, is never the same as a continuous wave plasma. And usually what I say, the plasma you have when you pulse usually is more molecular than atomic. And so this may induce, can be benefit. And what is the most important parameter when you pulse? Usually it's not the frequency. We observe that frequency has not so much impact. Going from 1 kilohertz to 5 kilohertz is not so important. But the duty cycle is very important for and has a strong impact on the plasma etching process. So benefit of pulsing the plasma is that you have more additional knob. You can modify the plasma chemistry and ion energy and distribution with time, what you could not before. So now you can modify the time. And now you can combine low dissociation and high ionic flux. But since you have more parameters, you increase the complexity of the process. And usually for regarding throughput, if you pulse, if you have less time on, so less time of RIE, energetic ions with radicals, so usually you observe a decrease of the etching rate. Okay, so here, this is what we have by pulsing the plasma. Now we use HDP source to decouple, and now we pulse HDP source. So if we pulse HDP source, we decouple, but we also vary with time ion flux energy and vary with time the radical to ion flux. But the radical flux is still constant because I said the radicals survive more longer than the off time. So we do not really modulate the radical flux by pulsing, and temperature is still constant. So the question is, can we now modify the process to also pulse the radical? So this is where we go from RIE with continuous etching to processes like atomic layer etching. So I took the design of a HDP source where you have the power source and the bias power. So all is continuous. First generation of reactor, you remember, the power is continuous to the source. We have a continuous power applied to the bottom, and the gas is introduced in a continuous way. Now we started to pulse the RIE process. So we pulse the plasma. So we can pulse the source, we can pulse the bias, and we can now have a variation of the ions to radical. But the radical is still constant. And you can really imagine that the next step is to pulse now the radical with time, to not have the radicals only introduced in a continuous way. And so we have sometimes we introduce the radicals, sometimes we don't introduce the etching radicals, and sometimes we introduce the molecule CL2, and sometimes we don't. So now we can also imagine that we can maybe pulse also the radicals or pulse the ions. So we not only modulate the ion flux, but maybe we can vary the ion flux with time by pulsing the gas. And if we pulse the gas, and if we have HDP source when we only apply power to the source when we have radicals, so we have a chemical etching, we have a sort of a radical etching process. We only throw radical to the surface, and then after we apply a bias to have energetic ions. So we have ionic flux with energy, and we can pulse to have successive step of radical ions, and this is where we go for atomic layer etching. So this is what we develop for atomic layer etching and the same design as atomic layer deposition, that we have two steps of reaction. So we pulse the gas, and during the first gas precursor, we use to modify the chemistry at the surface of the substrate. And thanks to the modification of the chemistry, we use a second pulsing to have energetic ions, and we do a sort of selective etching. We only remove the layer that has been chemically modified, and we don't remove the layer below. So we only remove, for example, one monolayer. If every time we modify one monolayer, at the end of the process, we only remove one monolayer, and then we repeat as many times as we need, depending on how many monolayers we want to remove. The same as for ALD, but ALD is the opposite. We want to add the precursor, and after we want to modify the precursor, not to remove one monolayer, but to add one monolayer, and we do the layer per layer deposition. Here we do layer per layer etching. So this is ALE, atomic layer etching process. This is ALD. So this is the idea that we have 4 steps for both an ALD and ALD process. And for ALD, we try to understand how many growths we do with one cycle. The sum of the 4 steps is what we call growth per cycle. And usually it's about 1 angstrom per cycle, 1 monolayers. And every cycle you will add 1 angstrom. So you control the growth by the number of cycles. And for ALE, we try to remove 1 monolayer per cycle. So we try to estimate how many etch we do per cycle. This is what we call APC. And for example, the same order of magnitude could be, for example, 1 angstrom per cycles. And you can see the same ALE process where we try to remove 1 monolayer per cycles. Regarding semiconductor industry, we use more and more ALE, but ALE is more complex to develop, because an ALE is a sum of 4 steps, and we have n cycles. So it means that to optimize your ALE process, you need to optimize all the steps and the cycles, while it's only 1 step of optimization for RIE. And ALE is very slow. So it means that for throughput is not good enough. So we can try to imagine, can we try to find something between ALE and RIE to have a sort of pulse RIE where we pulse the plasma and we pulse the gas that could be like ALE-like. And so we have the advantage of ALE and we have the advantage of RIE regarding the complexity and the time of the process. So can you reduce the process time? This is what I will try to show you. So this is basic ALE process we use with plasma. So we can do thermal ALE, but today I will not talk about thermal ALE, isotropic ALE. I will only talk about the anisotropic ALE because we talk about reactive ion etching, which is an anisotropic process. So for anisotropic ALE, usually we have two steps of surface modification. You have a first step, surface modification. For example, we do chlorination. So we do a chlorine plasma, or you can flow chlorine gas, but usually we do chlorine plasma. Then we have a third step. So we have no more plasma just to remove the chlorine. And then we have the argon plasma to bombard with ions to remove the modified layer. And then we have, this is the activation steps, what we call a directional removal. So it's a directional plasma ALE. And after we have the purge to remove and when you repeat. So this is what we do. And you can see that the plasma ALE process or directional ALE is based on two processes, surface modification with a gas and ion sputtering. So this is what is illustrated here. We do chlorination and we sputter with ions the film that has been modified. So why do we only remove one monolayer? It's because the binding energy for the silicon atom in the bulk and the binding energy for silicon bond, which is bonding to chlorine, is not the same. So usually here we have a weaker binding energy for a silicon atom at the surface when we do chlorination than in the bulk. And you know that the sputtering threshold, when we do sputtering, depend on the binding energy of the material. So if we have two different binding energy for this top silicon atom and the bulk, we have two different sputtering thresholds. And what we have to optimize, we have to optimize the ion energy to be in between the two sputtering thresholds. So we only sputter the first monolayer and we don't sputter the second monolayer. So what is illustrated here? So when we do the modification of the first surface layer, we have a given sputtering threshold and the silicon atom in the bulk don't have the same sputtering threshold. So if we come with the ion energy in between, we should remove only this atom at the surface, and we should not remove the atom in the bulk. So we have an optimum ion energy to select. If the energy is too low, we do not remove this atom, so we don't etch. If the energy is too high, we sputter also the bulk, so we don't have a self-limiting process when we remove only one monolayer. So what is important is how you can modify the surface energy compared to the bulk. So you have to look at the bond energy, and in this table, you have an idea of what is the binding energy of the different atoms. And you can imagine that atoms that have very high binding energy, like, for example, tantalum, tungsten, ruthenium, we may have a huge contrast between the surface binding energy and the bulk. So it will be easy to have a LD window with the energy. But if you have some material like GE, who are very low binding energy, even if you do chlorination or fluorination, you will not have a huge contrast. So it will be difficult to sputter only one monolayer and not the bulk. So here's an example for silicon. So for silicon, if you have only silicon atom in the bulk, the energy is 4.7 eV. But if you do a chlorination or fluorination, you reduce the binding energy. So you will modify the sputtering threshold for the atom at the surface that are bound to fluorine to the atom in the bulk. So I took here the example of tantalum. Tantalum is very nice because we have a huge contrast between the surface binding energy if you do chlorination and the bulk. So the difference is very high. So you have a large window of energy for which you can sputter only the tantalum atoms that are bonded to chlorine, and you will not sputter the tantalum atom in the bulk. Okay. Now with ALE, the main issue is that if you want to do a selective etching, so if you want to do selective etching, for example, depending on which material you want to selectively etch versus another, you need to sputter one material and not the other. For example, if I want to etch silicon selectively to gallium nitride, all my ions should come with an energy between 40 and 50 eV, ideally. Or if they come with less, I will not sputter any of the material. If I come with more than 50, I will start to sputter gallium nitride and not be selective. So it means that it's very challenging, and we have to think about the bias waveform we use for directional ALE, because, for example, most of the waveform I've shown you we don't have a narrow distribution. We have a more or less large distribution, and remember, it depends on the ratio between the frequency of generator of the ion plasma frequency. So if here you need a very narrow distribution if you want to perfectly etch silicon versus gallium nitride with the ALE process. So now I will try to show you how we can modify the ALE process to make it more compatible to throughput. So what we do in the fab, for example. So what we can do in the fab, instead of having chlorine plasma, argon plasma, and we purge in between, we have no plasma, we can keep the plasma always on. We only pulse chlorine at the first step, argon is always on, and then we pulse the bias. So we pulse both chlorine and bias. That's all we do. So here we have chlorine plasma. We'll know low energy because there is no bias applied. And here we have only argon with energy controlled by the bias power. And so we can do the plasma ALE process. But if we want to go faster, we can also simplify, and you can try to no more pulse the chlorine, and we only pulse the bias, and we play with the duty cycle to try to have a ALE-like process. It's more challenging because since at the same time we have chlorine and argon, we may have RIE process, is what we have usually with RIE process. So you have to find an ideal duty cycle and an ideal frequency to, during this step, not go to the RIE, but to have a self-limited atomic layer process. But you can find some paper where people were successful to develop an ALE-like process by only pulsing the bias. Here is an example of what we do, for example, for silicon oxide versus silicon nitride, and I took example of process from Tokyo Electrons. This is a fast quasi-ALE process from Tokyo Electrons. So we do the etching using fluorocarbon for all silicon-based oxide nitride. Remember, usually by RIE, we use fluorocarbon. So here is the same. We do an ALE-like process. They call fast quasi-ALE because it's not ALE, where the plasma source is always on. So we pulse the fluorocarbon when the bias is off. And when the bias is on, we have no more fluorocarbon. So here we do the chemistry, and here we do the removal. And here we don't do any surface fluorination. We deposit a very thin fluorocarbon layer at the surface. So it means that, in fact, we don't have a self-limited process, because as long as we continue to, if we increase the time of this step, we increase the thickness of the fluorocarbon layer. It's not self-limited. So it means that it's more a time control process, a thickness control process. So you have to optimize this step to optimize the thickness of the fluorocarbon to be able after to do your etching process through the fluorocarbon layer like any RIE. And so the etch per cycle will depend on the fluorocarbon thickness you deposit in the first step. And the thickness you deposit will depend on the time of the first step. So it's a time control ALE process, is not a self-limited ALE process. This is quasi-ALE. So this is an example. So if you want to selectively etch oxide versus nitride with this fast quasi-ALE process, so you pulse the fluorocarbon. And we know that when we use a fluorocarbon chemistry, depending on the nature of the silicon substrate, if it is silicon, silicon oxide, silicon nitride, we will not develop the same thickness of polymer. So for example, the thickness of polymer on nitride would be higher than the thickness of polymer on oxide. So that it means that when we do the removal step, we can still we can etch silicon oxide. But if the thickness is too high on silicon nitride, you will not consume the polymer during the etching. And so you still have some remaining polymer, and you will not etch the silicon nitride. So you may have a quasi-ALE process etching silicon oxide selectively to silicon nitride. So this is what you have. But after, when we do a fast quasi-ALE process with fluorocarbon, what is important to understand that we have some wall contamination with the fluorine species, and the wall contamination may add an RIE etching component during the removal step. During the removal step, we want to have only argon, but all residual fluorocarbon can be desorbed from the wall, bombarded by argon, desorbed and go there. So we may have an unwanted RIE process. So this may add some fluorocarbon combing, and so we may have a modification of the etching process. And we have some transient. To have the selectivity of oxide versus nitride, we need to first develop a thicker film, thick enough film on silicon nitride, and it may take some cycles to have the thick enough film of silicon nitride to do not etch silicon nitride versus oxide. So we may have some transient regime where we may start at the very beginning to etch also silicon nitride versus silicon oxide. Another design, and to simplify, the most we can simplify is the advanced pulsing from TEL again. So I keep the example from TEL, where we still have the atomic layer etching with fluorocarbon, but now fluorocarbon is no more pulsed. We only pulse the plasma, and we play with the plasma with the on-off of the source. So the source is on, the source is off. So when the source is off, we have only radical spaces flowing. When the source is off at the end, we have, at the low frequency, we have high energetic ions bombarding. So during this off step, we have energetic ions. During this step, we have no energetic ions. We have many radicals, and we play with the duty cycles. And we play with the duty cycle and the off here to control the dissociation rate, so to modulate the F etching agent versus CF2 depositing agent in the plasma, so to control the plasma chemistry. So it's an advanced pulsing, but you need to have a fast gas switching, so that will match the RF matching. So this is my last example. So you see for the second scaling area, we went from the HDP source when we started to pulse the plasma, and now we started after to pulse the gas, and so we can complexify even more the process. Now we are entering the third power scaling area. So for the third power scaling area, we have all is 3D. All is 3D, and what is important is that we need highly selective process. Highly selective process, but not only anisotropic etching. Now we know we need also to develop a lot of isotropic etching. So we will need to develop also plasma etching that will not be RIE, because the ionic assistance is for anisotropic. So it means that at the same time as we need to improve the RIE process, because we have high aspect ratio, high selectivity, so we need to improve the RIE process. We need to find a way to improve. At the same time, we need to maybe go away from the RIE process to go back to some spontaneous etching, radical etching process, because we need isotropic etching like for nanosheet. And what I think that will be the most important parameter maybe to try to play with is the only one right now I did not modify with time. From all the parameters, only one was kept constant. Remember, it's temperature. So maybe we'll see more and more process where I try to play with temperature. And maybe in the future, we should be able to try to modulate the temperature with time, but it's very difficult. So this is an example of where what we have now and what we try to develop for the next generation of etching. So some example can be the cryo etching. We have more and more cyclic etching where we introduce deposition step. We have to introduce non-sinusoidal power, so we have to change the RF bias waveform. So I told you, for example, we need to control the very narrow ion energy distribution. So maybe we have to go to RF to pulse DC, more and more pulse DC. We have to develop new gas chemistry because regarding the global warming, we have to find solution to replace some fluorocarbon gas, and it's very challenging. We have to play with for sustainability. We have to play with temperature, and we have to develop more isotropic etching like molecular beam or vapor etch. So first, I will talk about low temperature and cryo. So if I take the two components we have when we do the etching, we have radical flowing, so we have a spontaneous etching, and the spontaneous etching is controlled by the radical flux and the temperature, so radical and temperature. And we have the reactive ion etching, where it's more controlled with the ion flux and the ion energy. And to modulate the ion energy, the threshold is what we use, for example, for selectivity in plasma ALE. If we have a spontaneous etching, we can say that we can play with temperature to try to tune for selectivity. So if we have isotropic etching and more, maybe we have to play more with the temperature to modify the selectivity. And one example of playing with temperature, so temperature is not varying with time, but we do the opposite of what usually we do for the etching. Usually when we do an etching process, we want to favor the desorption of want to form volatile byproduct. And since the desorption is an Arrhenius law, usually when we want to etch, if we want to increase the desorption, so increase the etch rate, we go to high temperature. So when we have a plasma process, usually we say that if we go to low temperature, we favor condensation, so deposition. And if we go to high temperature, we favor etching. But in fact, it's not always true, and it depends on the nature of the radicals flowing to your substrate. And you may have radicals that will come to the substrate and will physisorb to the substrate. And again, the desorption of the physisorb species is an Arrhenius law. And so if you lower the temperature during the process, if your species are like fluorocarbon, if they can easily condense, if you go to low temperature, you will drop the etching rate because you will favor deposition. So if you have a C4F8 process and you go to very low temperature, you will increase the thickness of the fluorocarbon layer. And at the end, even with ionic assistance, you can no more etch. You have a too thick polymer. So you stop the etching. So it's not good. But if you have some gas that will not do any condensation, that will only physisorb, and if you can have only 1 or 2 monolayers of physisorption, then the etching gas can stay more longer at the surface. For example, if I take HF molecule, if you go from room temperature to -60, you will increase by 1,000 the lifetime of HF molecule at the surface. And if you increase the lifetime of this HF molecule, so etching gas, then when you add ions, you will increase the etching rate. So it's very nice. So this is what was proposed, for example, in 2023 by Tokyo Electron, when they said, we develop for the high aspect ratio for 3D NAND, a new process where we use a very low temperature, so cryo etching. And using a cryo etching, we can do the high aspect ratio etching, and in addition, we can reduce by 84% the use of the gas, so it's better for global warming. So because when we use the cryo etching process, in fact, they can enhance the etch rate, so they etch faster, and they have a very good selectivity, as they don't have the issue with too much fluorocarbon deposition because they play with the physisorption. So I took this illustration from the papers they presented here in 2023. So from the paper, you can see they use a CCP reactor. So you can see the design with the dual frequency. Remember, high frequency to control the plasma density, low frequency to control the ion energy. So they have the CCP. And what they do, they did a CF4H2 plasma. And when they do the CF4H2 plasma, what they observe, that if they do the process at room temperature or nearly room temperature, when they add hydrogen to the CF4 gas, they reduce the etching rate, what we can easily understand because CF4 is etching, H2 is not etching, so fluorine is etching. So if you dilute CF4 and H2, if you have more and more H2, you have less and less etching agent, so you drop the etching rate. Okay, easy to understand. But if they do the same at -60, for a given hydrogen dilution, they increase the etching rate before dropping. And they increase the etching rate to very high value compared to traditional value at room temperature. So now they multiply by 2.5 the etching rate going to -60 degrees while they dilute. So if you compare this etching rate to this one, you have a huge enhancement of the etching rate. And to try to understand why, they did some plasma characterization, and by OES, they observed the emission of OH. So they observe that they have some OH in the gas phase, and with the mass spectrometry, they also observe that they have some HF in the gas phase. And so this is what they explain. So they said that when we do CF4H2 plasma, we form HF because we dissociate CF4 in CF3 plus F. We dissociate H2 in H plus H. So H atom will react with F to form HF. HF will go to the surface. And remember, if we go to -60, which is why I did this calculation, if you go to -60, you will increase by 1,000 the lifetime of HF molecule on the surface. And so if you have more HF, when you add the ions, if you have more etching agent on the surface, you will promote and enhance the etching. And in addition, they observed that they had some water. And in fact, it is said that the water is adding the etching, because we know that when we do HF vapor or HF etching of silicon oxide, if we add water, we have a catalytic effect. And this water promotes the etching of SiO2 with HF, promotes the bonding of fluorine to silicon. And then by the presence of water coming from the first etching reaction, where we form water, we enhance the etching rate. And with the ions, so you add the ions to enhance this reaction. So it's not, you do not use a temperature, use ion energy. And with ion energy, you promote this reaction, you enhance, and now you do a lot of etching of silicon oxide, forming SiF4. This reaction was also proposed to explain the fast etching with the CF4H2 plasma. So this is the idea. So this is what we call the first cryo etching tool, for example, the LAM 1.0 cryo etching tool. And for the 2.0 process, people propose to directly introduce HF and to do an HF plasma. Instead of using CF4H2 or SF6H2, we can directly inject HF in the plasma discharge. And they also found that if you add some gas like PF3 will also do a catalytic effect, and we promote the etching. And so this is, for example, the Cryo 2.0 system from LAM Research, where we have the HF and PF3 introduced for the etching, and you do the etching at minus 60 or minus 50 or minus 70 degrees Celsius. So this is where we are, and now LAM is proposing a Cryo 3.0, and probably they still have the same gas, but they don't say what they have inside. It's just maybe slight improvement. Second step of improvement of what we do for the next generation of etching. So we'll probably develop more and more etching where we add a deposition step in the etching step. And the idea to add a deposition step is to have some corrective step. So for example, you do your high aspect ratio etching, and you may have some unwanted non-uniform profile. So what you can do if you have unwanted non-uniform profile, because you have ions reflecting, for example, from the mass, so you may have unwanted non-uniform etching. So what you can do is that during the time of the process, you can add some LD step, and you can, depending on the LD step and the control of the LD, you can only deposit on the top. And so you can deposit here when you are losing some materials to try to redefine the profile and then to propagate a very good profile for the etching. So this is what this example was proposed from Tokyo Electrons, what they call the fusion process, when some LD deposition steps are introduced inside the plasma etching process. And this is the same example to see the improvement regarding the CD bias when they add some LD step inside the plasma etching process. So this is combining deposition and etch, and we are combining more and more deposition in etch process and etch process in deposition process. Another challenge we have is for the high aspect ratio etching is the control of the ion energy. So what is important to understand, when we do high aspect ratio etching, we want to have energetic ions coming to the bottom because we need to do the array at the bottom. But the ions, they come perpendicular to the substrate thanks to the bias, but they also have some lateral velocity because they have some energy. And so depending on the ratio between the two velocity, they don't have a perfect angular of 90 degrees. So you have some dispersion, what we call ion angular dispersion. And usually you can calculate this angle of dispersion that corresponds to the ratio between the sheet voltage and between the ion thermal energy. And so if you can calculate this angle, and the issue is that depending on this angle, you can imagine that most of the ions will never be able to come to the bottom. So if you want to come to the bottom for high aspect ratio, you need to reduce this angle. And so you can try to do the calculation of what should be the maximum angle for a given high aspect ratio. And you see that as you increase the aspect ratio, now the ion angular distribution must go from 20 degree, for example, to less than 1 degree, compared to 90 degree plus or minus 1 degree to be able to have ions coming to the bottom of the structure when you have an aspect ratio 140. So the only way to reduce is to increase the voltage shift. So it's to increase the bias voltage you apply. So it means that now we need to use plasma etching process where we have to apply tens of kilovolt to the bottom substrate for high aspect ratio to be sure that we may still have some energetic ions going to the bottom. So this is an example. And now you can say, okay, we can do it for RIE, but now it means that for high aspect ratio, we cannot have any ALE process. Because for ALE process, remember, we have a low energy where we want to be between two sputtering threshold energy. But if we have a low energy, we have a huge angle of dispersion. So it means that no energetic ions will come to the bottom in high aspect ratio. So ALE cannot be used for high aspect ratio etching. But we have some solution. One solution, for example, is to use bias square waveform. So instead of using RF, we can use pulse DC. And the second solution is to try to say, can we, for example, use energetic ions? Can we do an ALE-like process with energetic ions? And the answer is yes, since thanks to this paper, recent paper from Canaric, from Lam Research, Canaric shows that what is important for the ALE window is not the ion energy, it's the dose. Because you may have the same ALE window, and if you use very energetic ions, if you reduce the ion flux, so if you reduce the time of the exposure to the ions. So when we do a process assisted by ions, like when we want to add ions for ALD or when we want to have ions for ALE, in fact, what has been observed that what is important is not the ion energy, it is the dose. So you may have the same dose if you use high energy, but you have just to reduce the time. So if you have a short pulse of square DC bias voltage, for example, you can have a very high voltage, short pulse, and you may still have an ALE-like process in high aspect ratio. Here, this slide is just to show to you example of from this very recent presentation from Samsung. In the Samsung presentation, the last ALE workshop, they presented where they use plasma ALE, anisotropic and isotropic thermal ALE for their application. And they show that now, for example, they use for 10 different ALE process, here 3 different ALE process and one. So at the end, they already use 14 steps of ALE in the use of when they do chips, for example, right now they use 14 steps of ALE, and half are anisotropic with plasma and half are isotropic without plasma. And in the future, we need to develop more and more isotropic because we will have, for example, nanosheet. We need to have more and more isotropic. And this is the same slide for him to say that what they have to do in the future, for example, is to combine ALD and ALE. So as I said, to combine deposition and etching and to use different bias waveform to have narrow energy distribution. For the sustainability, it means that we have to plan all these parameters when we want to have a sustainable process. So we have to optimize for the future of the process regarding gas consumption. We have to use low global warming to understand the impact of the wall. So usually we have to clean the wall, or we have to control the nature of the wall when you do an etching process. If we can avoid the contamination of the wall during RIE, we don't need any plasma cleaning step or plasma seasoning, so we can reduce the number of steps. So we have to improve abatement. So this is where we have to work for the future regarding sustainability. And global warming, I just gave you this table just to understand that some gases that we are trying to use now and test for the future, we have two options. To going from CF4 to other, or C4F8 to other gases, we have some molecule where we add iodine, for example, or some biggest fluorocarbon molecule. If we use biggest fluorocarbon molecule or if we add iodine, we can reduce the lifetime in the atmosphere, so it's better for the global warming. My two last slide will be for example of isotropic etching. So if we want to etch now for nanosheet, we need to have isotropic etching. So it means that we need to develop more and more vapor phase etching of molecular gas phase etching. So it's not good for RIE. We no more use ions, but people working in industry on etching system need to develop new equipment to be able to do the selective isotropic etching that will be needed in the future. And this paper is a good example of how we can do this nanosheet etching using a F2 gas. And this is an example I took from Tokyo Electron again, from what you can find on their website with investor relation, just to show you this example of the tools they try to sell now. So if you look at Tokyo Electron, for example, they have what they call a gas cluster beam system, where they use a gas cluster beam system to try to have a better control of the ion energy. So they want to etch not with very big molecules, a cluster of ions, to try to have a less impact regarding the lanet roughness and roughness due to the ions. Regarding logic, DRAM, and NAND, they have to develop some specific equipment. And for example, they have to develop new equipment where they can go from RF bias to pulse square bias. As I said, it's what they call the HERB for their technology. Because if you have this pulse DC, we have only energetic. If we have RF bias, we have low and high energetic ions. So the low energetic ions, we have large ion angular distribution. Only the high energetic ions will come to the bottom. If we have a DC pulse, we have only energetic ions, so they all come to the bottom. So we try to remove this distribution to come to this one, to remove the low energetic ions that will not go to the bottom. And we try to improve our high aspect ratio with radicals. So this is the tools they use for cryo etching. They call phase. This for phosphorus hydrogen-based phased ion etching. This is a cryo etching I explained with HF and PF3, you see, where we do the cryo etching. This is their equipment. And you can see that for nanosheet, for isotropic etching, they develop gas chemical etch to try the nanosheet etching. So the tools they try to develop now is an illustration of what I said for what we need to develop for the future. So to conclude, this was the first generation of plasma etching reactor where all was coupled, nothing was varying with time. So after we use a second generation like dual frequency and HDP source to uncouple two parameters, but now all was still fixed was not varying with time. After we had the third generation when we pulsed, so we pulse the gas, we pulse the plasma to uncouple all parameters and to vary with time the ion flux and the ion energy and the ratio between the radical flux and ion flux. And last generation that we pulse not only the plasma but also the gas. So now also the radical flux is varying with time. So it should be time, not Tom. But still the temperature is constant. So now we have new process where we try to understand the impact of temperature, like cryo etching, but we don't have process where we can vary with time. And to my knowledge, there is only one tool that's very interesting from Hitachi, where they have some infrared lamp, so they can modulate the temperature during the time of the process, because if you want to modulate the temperature with a substrate, it takes very long time under vacuum to go from high to low temperature, so it's not possible. But they use this infrared lamp to have an additional heating, so they can do an ALE process where they flow some gas to do an NSF film on the surface, this solid film, and after they use the infrared lamp to heat this material and to volatilize these materials, and they repeat, and they have an ALE-like process, and by playing with the variation of temperature with time, so we don't have the same temperature here than here, because we use during this process the infrared annealing. So this is a good example of how we can try to add new processes by varying temperature with time. So I think it was quite long, 1 hour and a half. So this is my last slide. So I would like to thank you for your attention. And next year, I'm sharing the ASD workshop in Albany. So if you want to understand area selective deposition, you are welcome to come to Albany and to discuss with me. And I'm also sharing the ALE for the LD-ALE workshop. So we have a workshop every year. And this year, the LD-ALE workshop will be in June, in end of June, the beginning of July in Tampa, Florida. So thank you. So if you have any question, you are welcome.
Thanks, Christophe. That was a very comprehensive overview. Thanks a lot for volunteering to doing this webinar.